All right, let's go ahead and take a look at today's lesson, the natural base E. So you got to do a little explaining about this. You go ahead and read that paragraph. But this letter E is much like I and pi. It's a symbol for a number. It's not a variable. It is it's a special number. It seems to occur a lot, quite often, I should say, in mathematics. And we need to learn what it is and how to calculate with it today because we are going to run into this number quite a bit in the future. So I want you to be familiar with it. So as you can see in the graph, there's a picture of a function that models this situation. And if you were to take this function, I'm going to go ahead and highlight it right here, and substitute these values into it one at a time, what you would notice is that these values would start, and that would be 10, 100,000, etc., 10,000, 100,000, reaching a limit where they're converging upon a number and getting closer and closer and closer to it. And that number is the number that we refer to as E, or Euler's number is the name of this. So here it is. That's the approximation for E, and it's actually a number that's on your calculator as well. If you search for it, you'll find that cursive letter E on your keyboard. Now, like I said, that number seems to be a transcendental number that spans across the spectrum of mathematics, just like pi. So we need to be familiar with it. Let's go ahead and try to calculate some things with it. So what I'd like to show you is how to calculate with E, and then I'd like you to try some examples yourself. So part A, for example, if you're going to calculate with E, what you do is you treat it like a variable. Now, if we multiply two bases together, don't we add exponents? We do. So this would be e to the 3 plus 6, or in other words, e to the ninth. Let's go to part B. In this case, since we have fraction, right? 16 divided by 4 is 4. And then do you remember what we do with these letters that have the same base, both of these e's? We subtract exponents, don't we? So e to the 5 minus 4 would be e to the 1. So I guess there'd be a 1 there. You wouldn't even need that. This would be 4e. So the theory is keep treating this like as if it's just a normal variable. How about part C? This is the power rule, isn't it? So what we need to do is apply that exponent to everything. So 3 squared is 9, e to the negative 8x. But that's a negative exponent, isn't it? So what we want to do is think of this in terms of a fraction. So this will be 9 over e to the 8x. So we got to remember, when we're simplifying expressions, we should never have any like terms remaining. We should never have a zero exponent. We should never have a negative exponent. All right, I'd like everybody to try those three by themselves. Let's go ahead and take a look at your answers. For number 1, you should have added your exponents together to get e to the 11. For number 2, if you reduce your fractions correctly, those numbers 24 and 8 would divide to give you a 3. The e's will subtract to give you a 3. And I don't think we need a fraction, do we? No, we don't. So I guess we could just get rid of all that and say, there we go. There's our answer. All right, let's go on to number 3. Looks like we got a power rule here, don't we? So that exponent of 3 is applied to both. So this will be 10 to the third e to the negative 9x. And then we could think of this as a fraction, right? So what we could do next is then 10 to the third is 1,000. This e term would move down here, wouldn't it? And it would be a positive exponent then. I messed that up. So let's go ahead and do that down here. So this would be e to the 9x. And there we go. We've got our answer there. All right. That's how you calculate with e. Now let's look at an application of it. So there's this concept of continuously compounding interest. So we had talked about compounding interest in the last lesson, where it could be compounded like yearly, semi-annually, quarterly, monthly, etc. Well, what if, theoretically, what if we could compound interest instantaneously every moment? Well, what this does is it unlocks a lot of financial formulas that we're not going to have time to discuss. But it's an interesting concept that I would like us to visit. And there's your formula right there. Let's go ahead and apply this. Let's look at this situation here. You and your friend each have accounts that earn annual interest compounded continuously. All right, so that means Euler's number. The balance in dollars of your account after 2 years can be modeled by this equation right here. That's for you. The graph shows the balance of your friend's account over time. So let's look at this graph. Looks like it's going upwards, right? What's this question ask us? Which account has a greater principal? Okay, so the principal is your starting amount. So yours is $4,500. Your friend's starting amount is a y-intercept, is 4,000. You have a greater balance. Okay? Look at this. Which has a greater balance after 10 years? Well, let's look at this graph first of all. After 10 years, let's see here. Here would be 10 years. I hit the graph about right there, and I'm going to go over there, and I'm going to say that's a little bit more than $7,000. Let's say $7,200. Let's guess at that. Let's see what your account would have after 10 years. All right, so I think what we're going to do is we're going to go up here, and we're going to use this. And what we're going to do is we're going to replace the t with a 10. So this is going to be A equals 4,500 e to the 0.04 times 10. And then we're going to get an approximation of this. So let's get the calculator out. I already forgot what that was. 4,500. Now everybody look for the E button on your calculator. Mine is the second function of ln, which is what's called the natural logarithm. Now I'm going to be careful about this. I'm going to put my exponent in parentheses just so there's no mistakes. And I get about $6,713 approximately. So after 10 years, who has more money? Your friend does. So if we analyze this and look at this formula, he starts with less money than you do. So I'm thinking the only difference here there could be is that the interest rate must be higher for your friend, his account must be getting more interest. Let's do a follow-up question. Look at this. You deposit $4,250 into that account, in an account that earns 5% interest, compounded continuously. Compare that balance after 10 years. All right, let's try that. Here's the formula. Let's go ahead and put some information here. My principal, $4,250. So that's in between both of these situations. My rate, 5%, so that's 0.05. And my time is 10 years, which is the same as the other example. So I wonder where this is going to fall because the interest rate's a little bit different. And the principal is different. It's in between you and your friends. Okay, let's activate E. Interest rate is higher than yours. We don't know the interest rate on your friends, but it's the same time period. $7,007 approximately. And if you compare that back to you and your friends, I'd say it's pretty close to your friends. It's hard to tell exactly what your friends is, but pretty darn close to that. So that's interesting to at least analyze that situation.